All right, we are now moving into Unit 3, and today it is going to be a discussion on classification of types of stars. So let's start off with just trying to figure out what a star actually is. It's a large ball of mostly hydrogen and helium. Now, there can be many other elements in there as well, but hydrogen is one of the most important. It produces heat and light, and it is undergoing fusion. And we've talked about fusion already earlier in this semester, but that is one of the things that a star must be doing to be considered a star. They can survive from millions of years to billions of years, and they can range greatly in size, color, and energy. So, classifying. There are various ways to do it. Well, we're going to focus on our three different things. One is temperature, the other luminosity, and the other is absolute magnitude. Temperature is something simple that you've heard of before. It's the surface temp. It's basically how hot is it right at the surface. Blue would be the hottest stars. Then you've got white, yellow, orange, and red being the coolest. Luminosity is how bright the actual star is. So it's kind of like how they measure light bulbs when you buy them. How bright are they? Absolute magnitude is a little bit different. It's how bright it appears to be when viewed from the Earth. It's not the actual brightness. So what that means is you could have a very luminous star that's a long ways away, and it's just as bright as a less luminous star that's closer. They would appear the same in the sky, but yet their luminosities are very different. This is called the Hertzsprung-Russell diagram, and this is a very interesting diagram that shows where most of the stars are for most of their life. You'll see this band going down kind of from the bottom right corner up to the top left corner. That's called the main sequence. That's where most stars spend most of their lives. Then you've got some white dwarfs and things that are down in the lower left, and you've got some of the larger stars up at the top. Now, if you look at the two axes, you'll notice on the left-hand side, the vertical axis is absolute magnitude, so that's the brightness. And on the right axis is the luminosity, so how bright the star actually is. Then across the bottom, you've got temperature, and you'll notice that on the left, you have the blue stars, and on the right, you have the red stars. And in the middle, you have white and yellow, because those are all your kind of mid-temperature stars. So, there are different spectral types of what are called main sequence stars. They're ranked from largest to smallest, hottest to coolest, brightest to least bright, and least abundant to most. So you've got the O, B, A, F, G, K, and H. We're not going to spend a ton of time on this, but just so you realize that the O's, B's, and A's are all blue. They're the hottest. F's are blue and white. G is white, yellow. K is orange, red. H is red. Just something that you can go back to as a reference. So here is some information on main sequence stars, and you'll see that the blue, working its way down to red, you can see that the temperature decreases as you go along. You can also see that the radius also decreases, and so does the mass. So there are some different things that you can see that are kind of, that are consistent. Then down here we have the giant stars, the white dwarfs, and supergiants. So giant stars are large. They're large. They're generally pretty hot, but they're big, 10 to 50 times the radius of our sun. Over here you have the supergiants, which are 30 to 500 times the radius of our sun, and much, much more massive, 10 to 70 times more massive. These are the ones that will have deaths that are a little bit more impressive, you could say. Okay, there's different luminosity classifications. So again, not something you need to memorize, just something that's here for, so you understand that this is another way that they classify things. So you've got the 1A, 1B, 2, 3, 4, 5, 6, and 7. So you start with the very luminous supergiants, ones that are giving off a lot of intense light. And then it works its way on down to less luminous supergiants, luminous giants, giants, subgiants, main sequence stars. That's where the sun is. It's in number 5 down there, or Roman numeral, 5, letter V. And then you've got subdwarfs and white dwarfs. So our sun is not terribly big and not terribly luminous. Main sequence stars are where most of the stars are. They make up 90 to 95% of the known stars. They are all considered dwarfs. So none of the giants and hypergiants and supergiants are part of the main sequence. The sun is a main sequence star. They're all undergoing fusion. And they're mostly fusing hydrogen because they're not that big and they're not that old yet. Stars more than double the size of the sun will start to fuse larger elements. So as they get a little bigger, then they can start fusing into heavier things. They range from cool red all the way to very hot blue. The sun is actually almost pure white. It's a little yellowish. It appears yellow because of our atmosphere. So when we view it through the atmosphere, it looks like it's yellow, and when it gets down near the horizon, then it starts to look, more orange. But that's because of our atmosphere. And you'll see that the Hertzsprung-Russell diagram, the main sequence is where most of the stars are. So again, here's that main sequence, right through here, and that's where most of the stars that we know of are at. So, star types based on size, you'll hear the term dwarf. That's a small star with temperatures ranging from red to yellow to blue. Most common are red dwarfs. That's actually the most common star there is a red dwarf. A giant star is generally about 10 times larger than ours. A supergiant is usually about 100 times larger. And a hypergiant, these are a little bit more rare, are about 1,000 times larger. So hypergiants are the real big stars. Then there's also something called a binary, and this is actually quite common out in space. Binaries are where there are two stars orbiting a common center of mass. So basically they orbit each other, and the center of mass is somewhere in between them. Wide binaries are stars that have evolved a long ways apart from each other, and they don't impact each other much, and they might have even had a third star that they were part of a three-star system. And they kind of orbit around each other, but they don't do much to each other. Close binaries are where things get a little bit more hectic and chaotic. They're close enough that they can transfer mass. So if one is more massive, it can actually pull the mass from the other one. And sometimes one can basically gobble up the other one completely. It can pull the star right into it because it has higher gravity. So this will end the first discussion about stars. And make sure you're filling out your study guide.